Okay, so last lesson we were talking about basic ideas of magnetism, and we were really just doing a GCSE recap. Now, the bit that I missed out from last lesson is this bit, the force on a current carrying wire. And I am going to assume that you remember that pieces of wire that have a current running through them placed near to a magnet experience a force. It's called the motor effect, and it was the basis of our study at GCSE of the rotational effect of how spinning motors do what they do. So I'm going to assume that you remember that bit. I am going to go over it now, but I'm going to go over it fairly quickly, and I'm going to focus on the A-level aspect of it. So let's make a start. So you probably remember from GCSE drawing pictures like this, where we've got a magnetic field that's a uniform magnetic field contained between two poles of either two separate magnets or a magnet that's been bent round into a horseshoe shape. It doesn't really matter as long as there are two poles. The magnetic field lines between the poles have been drawn parallel to each other, and they've been drawn uniformly spaced to represent the uniformity of the field. Okay, and then within that gap, we've placed a wire and we've put a current in that wire. And as I've drawn it here, the wire and the field are at right angles to each other. However, that doesn't have to be that way at A level, and we'll come back to that in a second. So you should remember that there will be a force on the wire, and the force will be perpendicular to both the current and to the field. So in this particular picture, if you imagine that the current is running horizontally and the magnetic field is running horizontally in a different direction, then the force will be vertical. This is an experimentally determined effect, but I've got a video for you later to demonstrate to you why it is that way. So we'll come back to that later. Okay, so you met this bit at GCSE as well, but without the angle in it. So let me just remind you of your hands. So this is the bit you should remember from GCSE, that you used your left hand. It's called the left-hand rule, or to give it its full name, Fleming's left-hand rule. And you arrange your hands so that your thumb is pointing upwards, your index finger is pointing straight forward, and then you take your middle finger and you make it stick out of the palm of your hand so that your two fingers and your thumb are all at right angles to each other. Now, at GCSE, we did make them be at right angles to each other, but actually, as you can see that I've drawn it here, it's not required that the magnetic field and the current are perfectly perpendicular. You could take these two fingers and bring them together to make a little angle between there that's not 90 degrees. That's where the angle up there comes in. We'll come back to that in a second. So you should remember first finger field, second finger current, and then your thumb is the thrust or the force. So this is the picture that you should probably prefer drawing to this one. I don't know, maybe you like drawing hands, but it's usually easier just to draw three axes. When you do draw them, try and put these little right angle things in here to give it that 3D perspective when you draw it. And then the formula for the size of the force states that it will be directly proportional to the strength of the magnetic field, directly proportional to the current in the wire, and also directly proportional to the amount of wire that is in the field. So I am actually going to show you a quick demo in a minute where we show the direct proportionality between the force and the current. It's very difficult for me to show you a direct proportionality between the force and the magnetic field strength because I don't have a very easy to demonstrate variable strength magnet here in the class. So I'm going to skip out that little bit. The length is a little bit intuitive. You can think that each little piece of the wire is experiencing a little bit of force. So hopefully it's intuitive to you that the more wire that's in the field, if every little bit of it's experiencing a force, then if we double it, then there's twice as much wire to be experiencing twice as much force. The sine theta is the A-level addition to this formula that wasn't there at GCSE. And it states that there will be maximum effect when the current and the magnetic field are at right angles to each other. And there will be zero effect if they're parallel to each other. It's there because we've resolved the current. But the question is, we've taken the component of the current that's perpendicular to the field. The question is, why is the perpendicular direction so important? And that's what's in the video that I want you to watch afterwards, where it talks about some quite cool physics to explain why the magnetic field is so very different to the electric and the gravitational field. Just to remind you, we had some really simple force laws relating the field to the charge. So force equals charge times electric field strength for the electric field, and force equals kind of gravitational charge, mass, multiplied by the gravitational field strength. These were really simple formulae for the last two fields that we met. But this isn't like this at all. We've got F equals B, which is like F equals E or F equals G, and then where we would expect the magnetic charge, well, we don't have magnetic charge. We've got I times L times sine theta. This is a much more complicated formula, and it comes back to the fact that magnetism, as I mentioned last lesson, is not a fundamental force of nature. It's an aspect of the electric force, which is why there's an electric current in the magnetic force formula. I could spend some time now going through why that is, but honestly, the video is about 6 minutes long and it's really well made and really well explained. So when we're finished with this today, if you watch the first of the videos that I've put on Google Classroom, you'll see an explanation for why there has to be moving electrons, why the movement is so important. And it'll also explain to you why the force is always at right angles to these things. So that's for you to watch in a minute. Couple of other A-level bits and bobs that I want to talk to you about. The first is that although this is an excellent phrase, magnetic field strength, and it replicates the language of the electric field strength and the gravitational field strength, historically, it has been referred to as the flux density for a couple of hundred years. And this is quite a cool word, I guess, flux. It's not a word that's in everyday life anymore. It's an old-fashioned word. And I guess because it's a cool term and physicists like it, they just won't let it go. They like the history that's associated with it. So it's not actually anything to do with forces. It's to do with the aspect of electricity generation. You remember from GCSE again, hopefully, that we use electromagnetism to generate electricity using electric generators. And we are going to study that in a couple of lessons' time. So when we come back to that, I will explain to you what this term flux density means and why it's there historically. But for now, while talking about forces, it is utterly fine to refer to this as the magnetic field strength. It keeps it in tune with these other two quantities that we're more familiar with, and it just keeps the symmetry intact. So I don't know why, I can't remember why we use a capital B for magnetic field strength, but there you go. So the B is our analogy to E and to G, and our force law, F equals BIL sine theta, is our analogy to F equals QE and F equals mg. Okay, let's talk about units. So when we had the units of the electric field, we just had newtons per coulomb. And when we've got the units of the gravitational field, we just got newtons per kilogram. Now, if we were to do the same here, we'd need newtons per whatever that is. And current times length is not particularly intuitive. It doesn't trip off the tongue. So whereas the unit of electric field strength never got named after anyone, it's just the Newton per Coulomb, and likewise the Newton per kilogram for the gravitational field strength, because it kind of makes sense and there's no need to name it. The unit of the magnetic field strength did get named after somebody because it doesn't have a natural trip off the tongue unit like newtons per coulomb or newtons per kilogram. There's what comes after the per. So the unit of the magnetic field strength is the Tesla, which I'm sure you've heard of in the context of cars. But before it was a car, it was a unit of magnetic field strength, named after Nikola Tesla. Okay, so we need to justify the size of the Tesla. There's no advantage to making up a unit if you can't give me a definition of what the unit is. So you need to understand that we can rearrange that formula. As long as we keep it at right angles, we don't need to worry about the theta. It doesn't have any units. So in terms of a definition of units, we can take the force and the current and the length of wire that's in the field, put them all at right angles to each other. And then what we're saying is that the magnetic field strength will be 1 Tesla if we discover that 1 meter of wire carrying a current of 1 amp experiences a force of 1 Newton. So that's what's written there in the sentence, and that's your definition of 1 Tesla. Turns out that a Tesla is a pretty big unit. Even I don't know, an MRI scanner, which has got an immensely strong magnet inside it, even an MRI scanner operates at 2 or 3 Teslas at most. You actually need, if you want to do any research and you want to put a human in a field of above about 3 Tesla, you need special approval from an ethics committee. So the Tesla is a very, very large unit. And it fits nicely with 1 Newton, 1 meter, 1 amp, but it's a little bit on the large side. So most magnetic field strengths that we deal with on a daily basis are sub 1 Tesla, often down in millitesla. Okay, that's the notes that I want you to write down today. And I've already said that there are some videos that I want you to watch, but I've just got a quick demo that I want to show you now to try to justify to you that the force really is directly proportional to the current. Okay, so what's going on here? Well, what I've got at the top, I think I have just upset the balance. Hang on a second. So just to dismantle it, what I've got here, this is a top-down balance, which has decided to turn itself off. Oh, we're back. So this is currently set to 0, and what we're going to do is make it think that something heavy is on it. So we'll start with some actual things on top of it. So that's just some wooden holders to hold a wire. So there's a wire which is just going to sit on top of the top-down balance, and the wire is plugged into a power pack, which is going to push a current through that piece of copper. So that's that bit. And then over here, what I've got is a magnet that's been twisted round into what's called a horseshoe shape. So the 2 poles of the magnet are facing each other with a gap in between. And what we're going to do is put the wire in between that gap, and that will allow us to do this experiment. Okay, we're back. Okay, so there's the magnet straddling the wire. Trying to get it so you can see both at the same time. this is in grams, and it's a really sensitive balance. So down at the thousandth of the gram and the hundredth of the gram, it's picking up all kinds of tiny little things, like the wire is sagging slightly as it straightens itself out, and that's just adding a little bit of apparent mass to it. So we're not going to worry very much about the last 2 decimal places here. We're just going to use the first decimal place. The balance is just a bit too sensitive for what we need. Okay, so all I'm going to do is I am going to put various currents through the wire. And as I put the currents through the wire, we'll just jot down what the apparent mass is. And I've got a spreadsheet set up ready for this. So what you're going to have to do is toggle between the spreadsheet that I'm sharing with you and the camera feed if you want to see the camera feed. So we're just going to put a little bit of current through it. I think maybe what we're just going to have to do to make this work is to just record the 127.5 there, and I'll just subtract it off all the other values. But I'll turn up the current. I was trying to get it so that you could see it without having to worry about subtracting off the numbers. It's just a bit more intuitive, but we'll see how we go. 28.7. So hopefully you would agree that that graph does look like a bit of a straight line. A couple more. And last one. Okay, there we go. So if you look at the graph on the screen, I hope you would agree that that's a linear relationship, and it does look like it's going through 0. And therefore, some supporting evidence for the force, which is obviously directly proportional to the mass, to be directly proportional to the current. I wanted you to see the experiment and the justification for the part of the formula, at least. What your job now is for the remainder of this afternoon, there are 3 videos on Google Classroom. One of them is just a cool demonstration of the magnetic field using iron filings, but rather than on a 2-dimensional piece of paper like I did for you last lesson, it's in 3-dimensional space as a magnet flies vertically and iron filings are in the space all around it. It's a cool video. So that's the first video. It's a couple of minutes long. It's just a bit of fun. The second video explains to you the origin of this force. So whereas for these 2 forces, I couldn't give you a justification. It was just an innate property of matter that charged particles attract each other and massive particles attract each other. It was just inbuilt into them. Well, this force law, like I keep saying to you, isn't fundamental. You can derive it from the electric force when the charged particles are moving. And that's what that video does for you. Absolutely not examinable, but definitely worth a watch because it's quite cool. And then there's a third video on there as well, which actually tells you where magnetism comes from. Absolutely not examinable. It's firmly university level and postgraduate level beyond that. But it's interesting for you to have a watch of. So if you want to watch those 3 videos, please do. But in terms of developing your understanding, what I need you to be able to do is to apply that force formula for the force on a current carrying wire. So in the textbook in chapter 23.2, there are some questions, about 5 of them at the end of the chapter, that I just need you to have a go at. Just pay attention to the note that I've put on Google Classroom. One of the questions, the graphic has been printed incorrectly. So the labels on the graphic are correct, but the graphic itself is not. So just be a little bit careful and feel free to modify your textbook in pen to fix the images.